Good afternoon, ladies and gentlemen, and welcome to the SAIEE Kwa-Zulu Natal Centre webinar on utility-scale solar PV in South Africa. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the KZN Centre playlist. This channel is updated regularly, so find the registration link in the chat box and register. It's free. A certificate of attendance will be issued a few weeks after this webinar, once we have received the CPD validation number from EXA. I'd like to introduce you now to our host this afternoon, Mr. Richard Alschlager, who is the chairman of the KZN Centre. He is a technical director for energy resources and manufacturing projects within Zutari. He is considered a multidisciplinary technical generalist on many aspects of power transmission, generation and distribution, and has the practical design and project management experience in both substation and line projects. He spent 10 years working for Eskom as a protection and technology specialist, primarily in protection, automation and DC standby systems, where he represented Eskom on several national working groups. Over to you, Richard.
Good afternoon, everybody, and welcome to the seminar. And I'd like to just introduce our speaker for today. It's Craig Knowles. I've used a little bit of nepotism, brought Craig in. He is a specialist on utility scale PV and various other forms of renewables, and has got quite a lot of extensive experience. So Zutari have been quite involved in a lot of the rounds of renewable lots that have gone out, working with a lot of international and local players. And I just do know that we're going to get a lot out of this presentation. I have had a look at the contents already, and I want to just thank you for taking the time to attend. Just I think another point of note is that we are going to be hosting our AGM directly after the session, and so I would like to encourage you to be part of that. If you're an SAIEE member, the SAIEE KZN chapter will be hosting its AGM. But without further ado, I think just a note that there are handouts in the handout section. I think Minx will also cover some of the protocols, but you are free to put questions into the question box on your GoWebinar. And after the presentation, we will open it up for questions. So without further ado, I'd like to hand over to Craig.
Thanks, Richard. So I'm just, I was slow in organizing my presentation modes. Can you see from my side now?
Yes, we can.
Great. Thanks, Richard. Thanks, Minx. Thanks to SAIEE for letting me chat to you guys today. I didn't tell Richard that I'm actually a member of the competing SAIEE, so sorry, Richard. I thought I'd bring that up now before we started. So today I'll just be talking to you about utility scale solar PV in South Africa. It's something in an industry that I've been in now since the very start of big utility solar in South Africa. So I'll just here taking you through just a general agenda. So I'll give you a bit of a background, maybe just a history recap of solar specifically in South Africa. And I think most of you, if not all of you, will have seen on the news and the various articles that come through how much innovation is taking place in the renewable space generally in South Africa. We're in a very exciting, very fast-paced industry at the moment. And as much as load shedding is a significant nightmare, it has opened a number of doors in this industry for significant innovation. So I'll give you a bit of an overview of where we've come from and where we're headed. Then I'll talk to you through the development process for big plants in South Africa, which were historically under the DMRE and REAP processes, but are now very much in the private uptake space. Then a brief recap on the technology and what we're seeing coming through and some of the new innovations that are coming around. Then as Utari, we do a lot of detailed design work in large solar and hybrid and the storage space at the moment. So I'll talk you through some of the considerations and how the process has evolved, I think, over the years to where we are now. I think that process is going to lead. And then my usual favorite, I think, is some of the lessons learned from this and some of the plants that are now well into operation. Okay, so if we talk briefly now through where we've come from, the industry really started of large-scale solar in the early 2010s or 2011 when the first REAP bid window was announced. Before that, there was a considerable amount of work in the background regarding the refits of the feed-in tariff schemes and how the Department of Energy then and government tackled emissions and tackled transforming some of the power sector. And that ultimately led to what has been a very, very successful renewable energy independent power procurement program, REAP 4PPP. So we then went through a number of years from 2011 through to about 2014 when bid window 4 was released, and there was a mad scramble. Bid windows happening in quick succession. It was really well received from market, and I think we saw a significant number of competition arriving in those early years. And then the unfortunate, call it the REAP gap between bid window 4 and now bid window 5 and 6, where a lot of the utility and governmental I wouldn't say interference, but lack of signatures effectively stalled the industry. And we sat with a gap for a considerable time until early into 2020 and 2021, following the RMIPP announcement, which is the risk mitigation program, and then ultimately REAP continued. And since 2021, this timeline here, we've had private generation thresholds lifted, and that really has just exploded. I think the big energy intensive users, the mines, big industry, the smelters, have really caught on to that. And you know, coupled with things like carbon reduction targets and net zero schemes, the renewable energy industry, and solar in particular, has seen a significant growth. So with that in mind, I was on one of the first REAP bid window 1 projects in South Africa, one of the big solar ones, and that's almost coming up to its midlife now. You know, those PPAs were 20 years, so it's now 10 years old. There's a lot of learning that's happened in those 10 years on those projects. And I think we're now starting to see a really new shape in this industry. With the removal of red tape, we're allowing some tremendous innovation to come through, and coupling with big storage systems, I think the hybrid nature of these power plants is really starting to produce some interesting results. Now, with that, REAP, through much of bid window 1 to 4, REAP remained fairly standard in its approach. It had set allocations for technology. You can see in the top right that was from bid window 1, 3, and 5, barring 5. The allocations were generally similar, and the approach was much the same. However, from bid window 5 and 6, and borrowing from the RMIPP program, the real grid capacity constraints started to come in. So REAP has since evolved considerably in bid window 5 and 6, specifically regarding the capacity. So you can build a much larger plant now, But then in terms of its ability to assist with variability in supply through things like the ancillary services with regulating ancillary reserve requirements, and then penalties associated with forecasting inaccuracies, just to enable that grid to be able to withstand a bit more variation in supply. Coupled with that, if we think back to bid window 1, we're about 230 watt peak modules. That was industry standard and as big as you got. And I think it's almost on a weekly basis, I'm seeing breakthroughs come through on some of the PV module publications, and we're well above 600 watt peak plus now in size, with their own challenges that come with the larger modules, which I'll talk to a bit later. But some of the other key sort of things that I think have led to this, we've now seen the ESI bid being released, which is the energy storage bid that's released this year. That private generation threshold has been removed, which is from 1 megawatt to 10 megawatt, 10 megawatt to 100 megawatt, 100 megawatt then removed. So really, the size constraint is no longer there. We are unfortunately left with the grid constraints, which is really our only real constraint at the moment before an explosion of solar goes up. And with that is the rooftop market, which is unfortunately many years late, but nevertheless we're seeing a lot of activity there. Okay, so then the targets. The resource in South Africa for solar is phenomenal. I think we are among the best countries on earth to exploit this resource, particularly in the Northern Cape. As you would all know, it's hot and dry and very consistent days. But that said, the rest of the country is not bad either. Richard, unfortunately, Durban is more on the low end side for resource, but nevertheless not bad by world standards. So the country really, as a whole, is suitable for solar. The ambition under the IRP, I took a few figures from the CSIR in terms of installed capacity and the ambition towards 2030. I think back to 2009, we were 0% installed. 2022, we're about 4% of total capacity installed with solar, and ambition to get to about 12% by 2031. This is a bit of a moving target, as much as we like policy in South Africa. And I think I just read just before this presentation that there is talks to extend the life of some of the coal stations, particularly the very old ones, which is an interesting choice given the cost, but that's aside. So just before I go on, the grid itself, so let's talk briefly about the issue around the grids. As you'll see from the top, this is taken from the Transmission Development Plan, which is Eskom's planning tool for South Africa. It gets revised every few years. And this broadly shows, if you take a look at our resource areas, the whole of the Northern Cape is very sparsely reticulated. These are the big interconnectors in and out of the province through to Gauteng and down to the Western Cape. So our grid has historically been designed around the load centers, so that's why all of the power stations are up near the coal fields in Mpumalanga, near Gauteng, and where the big load centers are, and then down in Cape Town around Kuburg and some of the gas turbines. Unfortunately, our best solar resource, as I said, is in the Northern Cape. Our best wind resource sits in the Eastern Cape, both of which are a little bit constrained at present. And I think there's now a definite shift to move upwards towards the load center while these interconnectors are strengthened. So there are plans for strengthening of the 400 kV network and 765s that connect the provinces, but those are quite long-term projects, and they are reliant on a number of factors like land, availability of permits and that sort of thing to get those projects through, which are quite long. Maybe with this in mind, if we look towards where our REAP projects have been, predominantly around the Northern Cape for the solar side. This is purely solar from bid window 1 to 4. You can see as bid window 1 and 2 took up a lot of the capacity around the Northern Cape, we pushed projects up towards Northwest. So Northwest is an area of particular interest at the moment. It's a bit cooler than the Northern Cape and not too bad, not too much less than the Northern Cape in terms of resource. So big drive there. Also big expansion plans in terms of the grid. Some big MTSs going up there with the bid window 5 projects that are currently under construction. 1 or 2 bid window 5s, or bid window 1s, excuse me, that are up in Limpopo, and definite interest up there as well. So Mpumalanga and KZN are the provinces that have had, I think, perhaps the least infrastructure or solar PV infrastructure built to date. That is swiftly changing. I think specifically in Mpumalanga, around those coal fields. So you will have seen Eskom releasing tenders and big tracts of land to private developers to facilitate a connection of renewable, not just solar, but wind as well, and storage in that area. So with bid window 1 to 4, we looked at an allocation of about just over 4,300 megawatts. Bid window 5 was 813 megawatts, and bid window 6 was 1,000 megawatts. That's just of solar PV. The big question mark has really been around private offtake. So this is all regulated and published on the IPP office, which has done a very good job over the years of managing these programs. But the private offtake potential is largely difficult to, outside of Eskom and the grid access unit, it's difficult to track how many of these projects are actually in the works. And there's an excellent conference with Eskom last month or month before, just with all the IPPs and the generators, just discussing one of the big hurdles in terms of grid access being how they allocate capacity on the network at various substations and on various lines to specific IPPs. And this graph, I think, particularly took my interest. It's the number of cost estimate letters. So that, for those of you who don't know, a cost estimate letter is what you apply for initially when you want to develop a project that will connect ultimately to Eskom's network, even if it's behind the meter. You would go to Eskom and you'd speak to the grid access unit and ask them what is required for you to connect your facility at that location. So this is for all the private offtake and REAP projects, and it's overlaid on the remaining capacity according to Eskom's grid connection capacity assessment, which is where they publish how much of this grid capacity is actually left in the country in the various provinces. So you'll see Northern Cape, Western Cape is actually negative, so heavily oversubscribed. But the number of cost estimate letters issued, which indicates number of projects of interest, are significant in those two projects, in those two regions. As we move out, as I said, Northwest, another area of particular interest since bid window 4. Still a lot of cost estimate letters coming through there. That's just from last year and from this year. So you can see the strength of that private offtake market after the lifting of this threshold is significant. There's, just reading off this, 57 gigawatts worth of cost estimate letters that have actually been issued since in just those 2 years alone. So the activity is significant. So with that then said, what do we need to build one of these plants? So first of all, we need an off-taker. We need someone to purchase that energy. It can be multiple parties with the new rules that have been lifted. We need land. This is a tricky one. We need rights to develop or own and lease that land. And specifically where that land is makes it difficult. The big one, as I said, the grid connection capacity. This is our biggest hurdle at the moment, is where we connect. So we need that input. Then obviously our permits, licensing and consents from the various authorities. That hasn't changed significantly other than talk around reduction of the EIA process and basic authorization for solar PV specifically. That's been gazetted by Barbara Creasy. Then obviously you need project finance to pay for it, and you need a contractor. So where significant innovation is happening is in the offtake space and project finance space, other than the engineering space. And I think that's more to do with the fact that now that we're allowed to build large facilities outside of the ministerial determination, there's now an opportunity for businesses to think outside of the box in terms of how that energy gets sold and wheeled across the grid. So wheeling, since I park my solar plant somewhere in KZN or Limpopo or somewhere else where there's grid capacity, and I essentially wheel my energy through the network to wherever my offtake is. So if I've got a factory in Gauteng or Cape Town or wherever it is, that energy then gets wheeled through. It's a paper exercise. It's not physical electrons that are going to be traveling from KZN to your plant through the wheeling arrangement, but it's essentially, as I think Andre de Ruyter said, we're using Eskom as a big battery, and that has really we've seen some very, very interesting ways of modeling this and making it bankable. Then the one area that does need some innovation, as I said, is the grid connection capacity constraints, which are largely within Eskom's remit, and that is a challenge. Okay, so then how this all works, if we are starting in a conceptual stage, we have an idea in terms of load that we need to supply. We have an opportunity for a big mine, a big industrial off-taker. We understand that we've got a big energy supply problem, and we either want to reduce the cost, we want to reduce dependency on Eskom, we want to reduce the effects of load shedding. So that's where our concept starts. At this stage, we need to go and start doing some prospecting to understand where we could build the plants, how big it would need to be, how we would connect, the basic fundamentals for any red flags that would arise right at the beginning before we follow the rest of the steps. From that stage, we then typically, now this is a typical development process. I should say that we've seen some clients that have, particularly in the private space, very eager to get a spade in the ground. So, if suddenly a pre-feasibility study becomes a feasibility study that becomes a bankable pre-financial close study. So these are flexible. This is the typical process that does get followed. And so with that, we move into the pre-feasibility study, which is just a bit more of a refinement of that concept. We start to look at the solar resource, get an idea of that energy, and some consideration of constructability around our sites. So by this stage, we'd usually have a number of sites to consider, and we'd go through a screening assessment here to pick out and choose what would ultimately be the best site to proceed with. From that stage, we start to get into the detailed studies. So now this is the feasibility side. Some of the clients call them bankable feasibilities, others detailed feasibilities. I've got a number of names for them depending on which industry they're in. And that's really where we start to get into how certain we are that this project makes technical and commercial and legal sense. So in that case, we're looking in detail at the energy yield from the plant, how it will actually interface with the grid. We start making applications through grid access unit if that's applicable. We start to take a look at the technology and decide what's best suited for that plant at that time. And then there's a big drive at the moment in terms of certainty on grid connection in this specific study. With that, in parallel, will be the assessment of the environmental impacts and then all the permitting and applications that come through with that. So once we've established from our feasibility side that we are okay, there's no fatal flaws, we think we've got a good project, we start to couple that with the tendering process. So historically through REAP, and this was really a requirement that came down from the lenders in those early rounds, because this was a technology that was new, it was niche, hadn't been installed in South Africa before. There was a lot of risk, or at least perception of risk, around the installation of this new tech. So the lenders had said, right, we need a single point of contact, a single point of blame if it goes wrong. We want to conduct this under an EPC, which is typically a FedEx Silver Book, fully wrapped turnkey solution, where you as the owner would then, if you're an owner, say, give them the specification, and they are free to operate within that to build the plant. I think that has now largely moved on, particularly in the wind space, actually, where we've moved towards split contracts, particularly there because you almost find that some EPC contractors struggle to wrap projects of this scale and size anymore with the demand. And when you're looking at, say, a wind farm, you've got the turbine component is a large part of the project cost when compared to the balance of plant side. So one of the contracting strategies that we've now moved into is called EPCM. It's Engineering, Procurement and Construction Management, which is more detailed on the engineering side on behalf of the consultant or owner, in which case we would essentially do the detailed design, or do down to a functional design and issue that to a contractor to build, and then ultimately have more control over how that plant is built, the standards to which it's built, and how it performs. The problem with EPCM, or at least what the lenders perceive as EPCM, is that risk allocation sits more towards the owner than it would with a single EPC contractor. But this has been executed. This was the old model that the mines have always used for their normal projects, so it's well understood in industry, but it's still reasonably new in our solar and wind space. Okay, so once we've started that process, we've got a couple of tenders out, and we're engaging with our contractors, and we're starting to talk to the lenders and the legal advisors to make sure that we've got a project model that works, and we've got some debt and equity ready to finance the project. We then move on to negotiations, and ultimately we'll get to financial close, fingers crossed. So at that point, financial close, we give notice to proceed to our contractor. The contractor will then go away and build the plant. If it's an EPCM, it's notice to proceed to the EPCM contractor to confirm or finish the remaining detailed design if it hasn't been done already, and issue that to the various contractors to install. And then during execution, which is key, is obviously the review of the design and supervision by appropriate engineers to make sure that that is executed well. So if we look towards the development process in terms of certainty, if we start at concept, you can see my uncertainty and profit lines fluctuate. My uncertainty, or my profit line fluctuates, my uncertainty reduces with time. So as I move through my feasibility stages up until FC, which would sit around here, my uncertainty lines decrease, and fingers crossed, profit remains on an upward trend. So we're a big proponent of doing upfront engineering to reduce the uncertainty and ultimately bring this uncertainty band down as soon as possible, because otherwise your spend is going to go up in this CapEx zone over here rather than a little bit of upfront engineering to quantify that risk. Okay, I think that's pretty much it on the development process. Then in terms of the technology, so I think PV modules know them quite well by now. They've been around for a number of years. Historically, we've had polycrystalline, monocrystalline, and thin film. Most of the bid window 1 plants would have been polycrystalline. I think those bid window 2 and 3 maybe had some monocrystalline. They were generally a bit more expensive in those years. And thin film, which is this niche technology on the side, it performs better in specific weather zones where there's high cloud, high water content. But ultimately, it hasn't been terribly widespread in South Africa. It's not as efficient, so you need more space for the same watt peak rating of the plant. And then I think entered the new tech, which is now becoming industry standard. You almost struggle to get monofacial these days. Is bifacial modules. So those allow sunlight on both the front and the rear of the module. And you'll get a slight uplift from that. As is expected, all the manufacturers promise the world, but in reality, not quite as much, I think, as you would hope. But there is an uplift, which I'll talk through on the next slide. With that, and with the innovation that is coming out of China with these manufacturers, and the explosion in size of the modules, we're starting to see non-standard physical sizes, which is causing headaches for the mounting structures and tracker suppliers particularly. In the earlier rounds, it was very standard. You have a 60-cell module or a 72-cell module, and that would have a rough designated size that wouldn't deviate too much between manufacturers. But these days, with these bifacial half-cut cells, 144-cell modules, the sizes are significantly larger in some cases, physically larger, so the tracker's needing to withstand a much bigger piece of equipment. But then everything else it becomes a bit more bespoke because it's now a much larger thing that you're supporting. And then, of course, there's an argument of P-type versus N-type, which is essentially the coating that you place on the silicon ingots. So it's all, you can see it on top of the module face here. P-type is a boron coating. N-type is more expensive. It's a phosphorus coating, and it's a little bit more efficient, which is why it's more expensive than the other modules, but you'll get a bit more power out of it. So really, it's as much as you want to spend defines what module you ultimately get. So then, in terms of what we mount this thing onto, bifacial modules specifically need a clearance behind and in front on the tracker system. So you can see this is a bifacial tracker over here, 2P. And essentially with the bifacial tracker, what we're doing is we're getting reflection off the ground, which impacts the rear face of the module, and you get a slight gain from that. Now, the challenge here, and this is specifically around modeling this and the yield, is that your site ground is going to change with time of year, between years, what you do with the land, and that has a significant impact on how much is reflected off into the back of the module. So I've heard some crazy stories of guys putting things like seashells on the ground, which whiten with sunlight and ultimately would reflect a bit more, and somehow don't trigger any environmental considerations. But anything to try and get that rear side gain up on these new modules. The other sort of issue I think with this is that, remember, if you shade a module, so if I shade one of these cells, I can get a hot spot because it acts like a diode and I'm blocking current going through that cell. And now that works hand in hand on the back of the module. So if I have anything blocking the back of the module, I also get a hot spot. So as much as you get some benefit out of it, there's some very careful consideration that you need to make about what's happening behind the module, so that you don't get some rude shocks in operations. Okay, then moving on to the mounting structure, which is, other than supporting larger modules, the industry has really settled, I think, on single axis tracking structures in South Africa. So the tracking structures would get a boost, so they will sit in north-south rows. They'll get a boost in irradiation because they'll tilt towards the sun in the morning, and they will get extra irradiation. So you can see that here on the side. So you get the fatter sides of your generation graph out of solar from the normal horizontal or fixed tilt system, which is in the middle. Trackers, of course, need a bit more space. The more space you have, the more energy you can get out of it. So that's particularly important for bifacial. So if I have a larger gap between the module rows, I'm allowing more light to reflect onto the back of the module and on the front of the module, which will increase my tracker gain and yield. Some considerations there that we need to make is in terms of cable sizing and what assumptions we make in terms of sizing, specifically the DC cables, because of that increase in generation potential. That's difficult to quantify. Yeah, so in terms of spacing, I think we're looking at about 2.5 hectares a megawatt for single axis tracking. Big systems, you can really put it anywhere on a variety of different landscapes. And I think often see in some of these presentations pictures of modules on the sides of mountains. Those are predominantly in China, and they're almost built on anything. Very impressive, but I'm not entirely sure that their energy yield is fantastic, but it's nevertheless quite an achievement that they can actually build it in places like that. Then I think another area where there is significant innovation happening in the tech space is the inverter side. So I'll start with string inverters. So we generally differentiate between two. We've got a string inverter and we've got a central inverter. String inverters really came from the rooftop space, but have now made significant inroads into the utility and very large scale projects. They're smaller, they plug and play, so you can just plug your string straight into it. They enable a better view of how your plant is performing, or can enable a better view because you've got string monitoring as almost standard on these units. Whereas with a big central system, you'd be needing to run string monitoring to your combiner boxes to see at that sort of level. Even then, it's a challenge to get to that level of monitoring. The drawbacks, I think, with string inverters is that they can get high losses because you've got more AC than DC. DC is better for loss. And it's difficult, as much as I said, there's a great amount of control that you can get out of these string inverters. It's difficult to, you still need to trench more, you need to install more comms cables to all the inverters. And when we're talking about processes with grid code compliance and retech, we're now looking at a much more distributed plant to control the output of by the power plant controller. So that PPC then needs to have a little more programming to enable it to operate a plant with a much, especially a large plant with a very large number of string inverters. Yeah, so those string inverters, we get your DC direct into the string inverters, and LVAC on the outside, typically 400 to 800 volts on the outside. Those will then run in trenches through to a power transformer kiosk, and you'd have your MV transformer in there, which is generally an 800 to 22 or 33 kV transformer, and then you'll have your medium voltage out to your grid connection substation, and then it's generally 132 or below or above that are out from that side. Some of the challenges I think that we've seen here is non-standard voltage sizes, which have come out of China, specifically from Huawei and Sungrow, voltages that are not common in South Africa. So insulation standards on cables, those kind of things need to be very carefully checked when you spec them to make sure that that they do actually supply the right cable for the purpose. And then also talking voltage, the next bit of fun I think is come from the mining industry, where we're looking at integration of these systems into existing brownfield projects, so big mines, big smelters, which are already operating on ring networks of 11 kV or 6.6 kV. So in those cases, and in some cases, we're looking at 6.6 kV overhead lines, which are carrying significant megawatts. So those conductor sizes are enormous to facilitate in that arrangement. So there is some learning, I think, that's coming now from REAP into the private space in terms of how you spec and optimize your plant configuration to make sure that you're not unnecessarily loading the system with losses, but you're still able to produce a reasonably cost competitive project. Obviously, with fiddling with voltages, you've got transformers and protection on either side, which needs to be facilitated, but the idea is not to have bespoke units at each power station, especially for spares. It makes it a bit of a headache. I think I've maybe gone over a little bit on that aspect, because central inverters also to talk about, and these have all been used on our REAP with window 1 to 4 projects. I can't think offhand of any with string inverters. Only the new ones are string inverters. So these are very suited for big systems, for very complicated layouts, and where you can run long strings of DC subarrays to your different parts of the plant. However, it's more complicated in technology. It needs some specialized technicians to fix if it breaks. In some cases, it's long outages if they need specialized parts to bring it back online. The difference here is that you've got a very large DC network. So your strings, which are the PV modules organized in strings, then run to a junction box or a combiner box, in which case they are then combined into what we call DC subarray cables. And those subarray cables then generally run in trenches to a central station, which is now called a power conversion station, not a power transformation kiosk. And in there would be your central inverters, which would sit on one side. You'd have a ring main unit and your MV transformer also within that container or on skids or plinths nearby. And there the inverters would then, it would come out as also 400, 800 volts on the other side, and then stepping up to the same 22 kV and network from there on out. So the MV side out is identical between the two configurations. So one point to note just about new technology, and this is specific to Sungrow, which is one of the big technology providers for inverters. They've got a new 1+X central inverter, which purports to offer the benefits of a hot swappable system, which is the benefit of a string inverter where you can just go and plug and play, but you can do that now with a string inverter, with a central inverter. So this technology is, I think we're going to see a lot of in South Africa, and yeah, could potentially be a game changer and must beat the battle between central and string inverters. Okay, with that in mind, so that's the technology generally. So in the design process, when we now start to look at building one of these or designing one of these very large plants, we would typically follow normal conceptual design, prelim design, and detailed design and issue for construction. Not always easy to motivate a client that we do need to go through all those steps, but nevertheless, that's the process that we follow. And I think the biggest lesson really that we've learned here, and what I would stress to anyone that's undertaking these designs, is to really understand your site and think the concept out properly. So your concept that you start the prelim design with is really going to define how difficult your life is going to be, not only in detailed design and specifically electrical design, but operations and maintenance of that plant. So if we, and I've often seen it, you'll get a client that will come with a concept and it shows us a complicated looking site from a land perspective that's just filled with modules. And they say, here you go, we can get this much out of the site, please go and design it. And that is a recipe for enormous pain and headache through design. We can't have 50 blocks each with a bespoke design. It would be an absolute nightmare to manage. So our approach is think your concept out first, get your technology nailed down at the start, or as soon as you can, given the variations and the configurations that come out of that, and then optimize it for shape and simplicity as much as you possibly can. And with that in mind, upfront engineering, I'm a big fan of, is to bring your project uncertainty down. So spending money initially will ultimately generally save you money down the line. So if we're talking about a new site, we would almost always say, get your geotech done before you appoint a contractor. That way you understand what kind of ground conditions you're doing. Your contractor is not going to price unnecessary ground risk in, and you're going to have some idea of what you need to design towards. Then the two, I think, that are still not done as often as we'd like, but we insist on it with our designs, is your thermal and earth resistivity readings for the sites. So soil thermal resistivity or conductivity defines what your cables are going to sit in. So how hot they're going to run, how much current you can run through them. And the sooner you know what you need to do in terms of not only cable size, but whether you need to either improve the soil conditions, which is very, very costly, or import soil, which is even more costly. the better. So that at that point you can have a real understanding of what your project is going to cost. So these two are quite dangerous ones to get wrong. The earth resistivity really links to your lightning risk assessment as well, in terms of how much copper you're going to need to put in the ground to make sure that your system is protected. And again, having that information upfront will aid you through the design process. To harp onto it, the layout being fundamental. What we like to do is to make sure that we stick and specify standards rather than bespoke requirements as much as we can. So there are a lot of standards, unfortunately, which lag the industry. So the industry, given that it is very innovative and it's a well-functioning system that is moving very fast, the standards lag it by a considerable amount. There's still a number of working groups, specifically on lightning. They haven't yet improved IEC 62305 or issued, I think it's part 5, which deals with lightning for solar PV. And we're now 10 years down the line in South Africa specifically, and that is still not done consistently between plants. And South Africa, specifically up north in Johannesburg and Gauteng, has very, very severe lightning conditions. So with that in mind, lightning risk assessment is key to get that done as early as possible. Know what you need to spec your equipment to, and ensure that it is done as such. Then with the design process, there's been a lot of innovation in terms of software tools which get used to do these designs. So SIMCAP is one that we use a lot of. It's cable design software, which is a finite element approach to sizing cables, as well as CDEG's earthing software. What's happened, I think, is with sites that have become more congested, sites that are a little bit more, maybe if I flick to the next slide, it's actually easier to see. So this is from our flagship project that we did a design for. Detailed design is now in operation. The issue with sites that are quite complicated in terms of shape means that you can be quite constrained in terms of how your cables run. So if we have a shape, and this shows a progression, and I'll talk you through that now of how we work through concept through to a block layout, and ultimately in the issued for construction set, what that eventually looks like. But if we have our inverters, let's say here, which are running alongside the northern part of this array and the southern part of the other array, I've got a lot of cables running simultaneously along trenches. And now SANS specifically doesn't deal with multi-layered trenches in terms of having cables on top of each other, different sizes, different types of currents running through them. It doesn't readily enable how you calculate that. And what we found is that if without using proper software like CDEGs to simulate how that cable is going to behave, you end up with cables that might clip in those trenches. So it's really important to understand your cable trenching and layout methodology using software like SIMCAP, particularly if it is a very complicated site, just to make sure that you're not going to get yourself into trouble with cable faults down the line. So that's a specific use case, I think, for SIMCAP. One of the other software packages that Zutari specifically developed with 7-Second Solar is a computational design software to optimize your block layout and your cable runs, which works hand in hand with software like SIMCAP, just to get an optimum layout, which is maintenance friendly for different technology configurations. I think then with that, the standards, some of the key ones, 62548, 60364, part 7, 712, these have been adopted by SANS, not the first one. So there is some standardization that's starting to come through, but it's generally between IEC and SANS that you'll find most of your guidance for these designs. EN standards, there are a few, but generally I think we've stuck to IC and SANS in South Africa and Africa. And then lastly, it's also the case with this project, when coupling with storage systems of big batteries, there's a number of considerations that you need to make, specifically around the concept and layout, because you're now dealing with another load sink on site, which needs to operate and communicate with your inverters on site. So this becomes quite a fun exercise with SCADA and communications to make sure that your system as a whole operates efficiently, and to make sure that you've got things like enough DC capacity on site to actually charge that system and discharge correctly. And that's some of the I think the really exciting projects that we're seeing come through with large scale solar plants. Okay, then maybe just quickly on how the layout and detailed design process would generally work. As I said, understand your site first. So we would generally take a layout of a site. So the client would give us a KMZ or a global mapper file, something which dictates where their land is that they want to build this thing, as well as any environmental information, geotech information, any other studies that are available. We then would establish a development envelope, which you can see by the green hashed lines here. In this case, there's some beautiful baobab trees which had a clearance maintained around it, as well as some conductors. I think these were 132 kVs coming in from the south and some from the north that needed some buffers. So once we've established a development envelope, we really can understand where and how we operate in our design. Then gets the fun in terms of iterating the concept, and at this stage is generally when the client gets quite involved in terms of what technology they'd like to see on the plant, and how the size and spacing and energy yield would work. So in this case, you know, we've refined it initially. If we looked at a tracker that couldn't be run, it wasn't independently actuated rows, so the rows were rigidly fixed into squares. It limits how much space and how much we can actually add to the layout in terms of DC capacity. So from that, we optimized in terms of what layouts or what technology we would use in such a layout, and then how the string grouping and inverter grouping would work to make sure that we were as efficient as possible and as simple as possible. So in this case, while it looks like there's a lot of different or irregular shaped blocks, in reality they're carved up into modular units, which make our electrical design much simpler. So in this case, you're looking at one detailed design for a block, one or two, and that readily enables a much more efficient design for operation as well. And so your as-builts for something like this is much easier than one that's entirely filled with equipment. Then I think ultimately we moved towards into our very final optimization end of a really fun design process, and settled on a nice tracker that enabled staggered rows and individual actuation, and we got a really efficiently designed plant out of it, while still kept the baobabs around the site, and managed to get, I think, a really maintenance-friendly plant out of the way at the end. So this is generally how we'd approach it. This is quite a difficult site layout to get the capacity out of, but ultimately following the process of ensuring that your concept is done effectively and efficiently enabled this to be executed quite nicely. Okay, then finally some lessons specifically related to South Africa, although it does extend up into Africa as well. As I mentioned in the beginning of the presentation, the policy certainty has been a real problem in South Africa. I think the flip-flop on what we are doing with large-scale private generation before the threshold was lifted and before this activity post-COVID really was very detrimental to the industry. Wind specifically, we had a factory close in PE that was designing and building wind turbine towers because of that lack of policy certainty. So now the government has put in place or enabled construction of very large projects. So that has definitely moved in the right direction. We just need to stick to that and not, flip-flop on programs and different ideas, because it scares investors, it scares the manufacturing industry away. So that's a really important thing from a policy side to look at. Secondly, SAND versus IEC and EN. SAND is actually a very, very robust set of standards. It's been well worked over the years. It knows South Africa's conditions very well. And we found in many cases that the SAND standards are more stringent than IEC and EN, which are generally built on kinder environments. So when speccing in South Africa, remember SAND is a legislative requirement for some of the standards, things like 10142, and it's important to make sure that reliance is not given, is not placed on European standards where there is a South African standard that is available. And then hand in hand with that is the lag between industry and the standardization process. I think it is catching up, but it's always several years behind in terms of what the industry is doing. To date, I think there's nothing on bifacial modules yet. Even for manufacturing guidelines, I think it's still probably IC test specs, not full standards. I'm not sure about that. Then highlighted in red, biggest lesson, South African climate. These plants are designed and built, need to be designed and built in South Africa, and places like the Northern Cape are incredibly harsh places to build things. And we find temperatures through the roof, soil difficult to build in, heavily calcreted in some places. And it's incredibly important to make sure that the design is done for the South African climate specifically. And with that is lightning. I think lightning damage in South Africa, and specifically in the northern parts of South Africa, is very, very significant, where you're getting upwards of 10 to 11 strikes per square kilometer per annum. We're talking about severe lightning. And unfortunately, a PV plant is really just one big lightning conductor. So making sure that we limit the damage or isolate the damage as much as we can with an appropriate lightning protection system design is absolutely required, and do that upfront and make sure that equipment is specified correctly. Then in terms of equipment obsolescence, this is a very, very important aspect for solar PV, and unfortunately it is the reality, is that I can't buy a PV module. I've really struggled to buy a PV module that's been installed on a bid window 4 project. So say a 330 watt module from Suntech, I would find it very hard to buy a number of those panels, because they are now obsolete and the manufacturers no longer stock them. They've now moved on to completely different modules. So this hurts the DC side particularly, so the PV modules and the inverters. Those round 1 inverters, no longer stocking that equipment, and now to go and rectify 10 years in is quite an exercise in brownfield engineering to get that done. Then lastly, I think the impact on technology pricing, that delay 2014 to 2019, 2018, while technology prices were decreasing, we just weren't building. And now, unfortunately, with silicon prices that have skyrocketed in China, as well as the transport costs, which I think went upwards of something like 400% in the last year or so, we're seeing, I expect we'll see the first sort of price increases with solar PV. We're already seeing it on the equipment side, so the modules have gone up quite a bit compared to, say, 2019 pricing. And certainty as to when that comes down again is difficult to prove. Perhaps one that's more affected is batteries and the price of lithium, which is very, very high at the moment, and struggling to see when that's going to come down because of the electric vehicle market competition. So really that means innovation in terms of new tech. And then very lastly, I think positive lessons that I've learned is the contract strategies are maturing substantially. So we're seeing new ways of building these plants through wheeling, through different private offtake mechanisms, different financing arrangements, and I think we're seeing some really great innovation in that space. It's something that Australia has actually been doing for quite a while in terms of the energy pool and buying off the spot market. And I think we're heading in that direction. We just need our grid to some work in our grid before we get to that stage, but it is certainly in the right direction. So it's a very exciting industry to be in, very fast moving, and keeps us on our toes. I think, Richard, I think that was it. Yeah, that was it from my side. Any questions?
Yeah, fantastic. Thanks, Craig. And very comprehensive. I'm ready to design and build my own utility scale PV now, I think. But I mean, it was really informative. We have got a couple of questions, and thank you for the effort that you put into preparing that. I see that you did go home and work an extra couple of hours. So appreciate it. And I think let's go through a couple of questions. I've got a couple, but I'll save those for later. And the first one is just around the presentation. So there is a recording of this that will be on the SAIEE website. And if you go down to your handouts, you will see access to various links that will then give you access to the information that you're looking for. We are also submitting this particular presentation for CRDB grading, and those that are CPD, sorry, we're doing a subcontract on the side, yeah, but yeah, so it'll be graded, and if you've registered for this, we'll have your email address and we'll be able to then send the certificates through. So that should, I've just answered the question in terms of the recording. It will be on the SAIEE site. And then in terms of, here's a question for you from Shane Engington. Sure, I know that name. In terms of the lightning risk assessment and LPS design, you've mentioned that the IEC standard has still not been updated. Hello, Shane. Do you see that the industry employers' requirements is flexible enough to allow for alternative or arguably more effective methods of designing an LPS system? So he's talking about the disconnect between that LPS IEC standards. Is there any flexibility in that, or are they going to hold you directly to deliver according to the law or the regulations?
So I think that the problem with that IC standard is that it's really a buildings regulation, or building standard. It was never designed, never written in the beginning for a solar plant. And a solar plant, because it's so, they vary in terms of how they are designed, it makes it very difficult to apply what that standard states to your design. So the guys that have our guys that do these lightning protection system designs have modeled a bespoke interpretation of that standard in terms of how you designated certain lightning zones. And with that, you can define what an acceptable loss is for a zone to be hit. So as far as I remember, they would designate a zone as the PV field, how much of the PV field would be struck, how much of that PV field would actually be hit, and what you needed to do to protect it. So one of the things that we are challenging, we've had some quite, I'll call it, robust debates with some of the manufacturers on these things, are the air termination rods for solar PV tracking structures, and how that effectively protects a tracking system. So initially we had challenged that in terms of physically fixing these air termination rods to the tracking structures that you were actually protecting. So the question came in whether or not you could have an appropriate separation distance where your lightning wouldn't jump into your panel and destroy it anyway. And there's been some debates around what those air termination rods are actually protecting, and how they do it on the DC system as a whole. And I think the outcome was, if the lightning is going to strike your tracker or near your tracker, it is very likely it's going to fry everything on there anyway. So some of the basics, I think, to get right are things like not using copper communication, making sure you can use fiber as much as you can, ensuring the basic insulation levels for your sensitive electronics are carefully adhered to, and making sure, I think if you can get away with wireless communications, because most of the damage is actually due to indirect strikes. So it'll be a strike that happens 100 meters outside of the fence, and it fries all of your sensitive electronics because it raises the voltage level on all of those structures. So the key really then is to make sure that you've mitigated that as much as possible. But Shane is right. I think the standard is still not there yet, and really in the lightning protection designs is still quite a moving target. But the basics are generally around making sure that things like your sensitive electronics and comms cables and things are protected as much as possible. And if you can use air termination rods, not necessarily attached to the tracker structures, but for protecting inverters and things like that, 100% go for it. I think the value is there. That's well proven. It's the niche part around the PV field that is still quite difficult to quantify correctly.
Thanks, Shane. Yeah, lightning is a challenge, and it's also linked back to earthing and all sorts of other things like that. I mean, also I've had a personal experience where I've questioned some of the validity of a specific standard. Went to SANS or SABS and challenged the standard, and then was informed that that's actually not a standard, it's a guideline. And suddenly there is a backtracking as to the relevance of whether it's accountable, yet insurance companies will then hold you accountable to the fact that did you implement according to this particular standard. So sometimes, yes, standards are fantastic, we need them, but we also need to understand the context in which the standard was originally developed, which is exactly what you're talking about. Has there been any movement on, for example, forums like SAIEE where they've addressed these things? I know SAIEE is quite progressive, and they often have these working committees which then will provide a response in some of these solutions. Have you had a chance to see that, any of that, Craig?
SAIEE, I know you're very familiar with SAIEE. I haven't looked specifically there yet. I know the IEC is obviously very heavily involved in that with the various working groups that are around. The two standards that I've mentioned, 62303, 62458, and 62738 were developed around about when Bid Window 4 was built. And some of the new designs were being done, and those were constantly in process. So that from IEC I know has been ongoing since the beginning. UL is another group, the Canadian standards, that is also quite prominent. A lot of theirs are directed towards the manufacturing standards, so UL will grade certifications around PV module manufacturer, tracker manufacturers, and that sort of thing. So they're more focused on the OEM market. But other than that, I think the working groups within SANS, within IEC, are just lagging a little bit behind the industry. And yeah, that is a challenge, I think, but it's the nature of the game with the new industry, I suppose.
No, thanks, Craig. I'm going to just move on to another question here from Riaz Asmal. Hello, Riaz. The question is around, are there any thoughts on using design tools such as helioscope to optimize the design of a PV system? And then comment on the limitations of such tools when developing designs, and if there are any other considerations that need to be accounted for when designing PV systems.
Sure. So helioscope, I don't use helioscope specifically. I think it's quite common in the building industry to use helioscope. So I've seen that used there a lot. Software definitely, and I think I mentioned it, is a big part of how we design and validate our designs. So for optimization and specifically around optimization of the PV arrays and cable networks, we'd use a combination at the moment of Auto PV, which is the offering from 7 Second Solar, which we developed with them, which optimizes cable route sizes, trench configurations, and cable routes for specific technology configurations. And then with that, we would use things like PVsys to ensure that the energy, or to check the energy for a given layout. But in terms of optimizing at the detailed design level, I think we would then have moved beyond a helioscope type approach and more into the bespoke tools, which are focused on optimal cable routes around the plant. But the helioscope's good for, I know for buildings, they've got a good offering. There's always something new that's starting, that's coming up in the industry, which is a challenge to vet, but yeah.
Craig, thanks. The next question is from Nicholas Burr van Skokwyk. Are there any new other technologies on the horizons that you are aware of that you could talk about or share? I don't know if he's talking specifically solar PV here, but I'll throw it wide.
I think, yeah, the new technology that excites me most is the storage side. So lithium ion we know very well, and the limitations of lithium. So I'm mostly interested in the equipment that will be coupled with solar going forward to smooth generation, to be used in proper time of use generation. That's what really I think interests me. And I am a fan of vanadium redox batteries, VRFBs, which are still in their infancy. There's not too many on a big scale that's being built yet, but they don't have the limitations of lithium in terms of the equipment or the cost of lithium specifically. So it's now got another rare earth being vanadium, which will drive the cost up there. But the degradation patterns are not like lithium. So your lithium batteries will degrade with time. End of year 10, you need to augment or throw it away, or it becomes very unstable. And the nice thing with lithium is that when it catches fire, you can't put it out. So those big battery packs have quite serious fire considerations. Whereas something like VRFB, a little bit different. You've got a very big electrolyte tank, which is where the cycle, the electricity cycle starts. You've still got inverters on the control side, so it's still able to respond in a similar fashion, but you don't get a degradation pattern as you would with lithium. So I think innovation-wise, the exciting stuff is happening on the storage side. There's things like salt batteries and all kinds of things happening, which university is probably quite an exciting place to be at the moment with some of the master's projects that are being looked at.
Anything on the next generation of solar panels?
Look, there was talk of organic panels at one point, and there still is, I think, of different materials. So it's generally around finding materials that are a little bit more conductive, generate a little bit more electricity. And in the lab space, the efficiencies are climbing quite rapidly under lab conditions for very small pieces of silicon and whatnot. So I haven't seen too much in terms of bankable new materials from solar PV modules that have come out. It's more around efficiency drives, purity of silicon, different module structures that have come out. And then of course there's other niche things like floating solar, and they're putting solar on roads and bicycle paths, which is quite fun. And that's generally a thin film technology, which has a few more different types of material like cadmium telluride, those kind of things. So that kind of space around adaptation of PV modules to unusual locations, I think, is also quite interesting.
So I'm going to throw you in the deep end here. Anything on superconductors? I know a big challenge that we're having is around the heating effect on the cables. I mean, any move towards a superconductor might eliminate some of that.
Richard, I actually don't know.
I'm not going to throw you under the bus. Let's leave this. No, I mean, maybe someone can present a paper
something up.
I think we have got. That's another one for another day. We'll bring that to the next presentation. So I won't do that to you. Apart from the softwares mentioned, what other PV and electronic or electrical software packages can be utilized for efficient plant design? I think we covered that to a certain extent. That's from Walter Mowa. Unless there's something that you haven't mentioned already, Craig.
No, I think there's a bunch of them. Things like PV cases is also another one. There's one from First Solar, which now the name escapes me, which I think is still around. It's like playing Tetris for a lot of these layouts, early stage software packages. But yeah, I think those are generally the big ones that we've used and seen.
Yes, I think I'm going to just make a comment here. And in terms of rational design, I think there's a note that every single software has its limitations. And I think it's imperative for an engineer to be critical about the tool that he's using. So understand the limitations of the tool before you use it. Otherwise, you can be very caught up in what we call design assumption that's embedded in the tool. So I'll throw that out as a warning. We're about good engineering, and that means understanding the limitations of the tools that you're working with.
Maybe as an example, that is interaction between civil works and electrical works on a plant. And we've had some designs where we get quite far away through and we arrive at a junction with a road crossing, a V drain, and a big combined cable trench running through. Civil says, well, how are you going to get through my drain? I can't move my drain. Electrical says, well, I can't move my cable, so what are we going to do? So those kind of things, the software packages won't help you solve, and that's really down to fighting it out in a boardroom amongst all the engineers.
A question here is that you mentioned a move towards string inverters for utilities. I think it was a move away from string inverters to centralized inverters. So do you feel that combiner boxes?
So there was not necessarily. So there's been a big debate for a number of years of string versus central. And string inverters are particularly useful for areas which are maybe difficult to reach, can't have big spares holding, a lack of technical skills nearby, where you can just order one, keep it in storage. When one fails or burns out, you just go and replace it, plug and play. But string inverters are limited in terms of how they, in terms of the design as well. So they don't necessarily react as well as a big central system to required voltage changes. There's still quite a lot of control infrastructure that needs to go in with that, and that becomes quite a headache if you're trying to control a field of 1,000 string inverters versus a field of maybe 10 big central inverters. Where there's a big, I think, potential move is towards central inverters that have now got the benefit of a string inverter approach for maintenance, which is the 1+X system from SunGrow, as an example, which they're called hot swappable. So you can, as I understand it, pull most of the inverter out and replace it, almost like a USB stick. Whereas that has never been possible previously. You need to disassemble it, you need to get a whole O&M team in to try and work out how the thing works, what to move, what spares to hold, whereas these are now centrals with the convenience of a string. So I think that might be where the market moves generally for big.
Excellent. A couple more questions. We're still on time. Just a comment here from Tian Stammen. Thanks for the presentation. It's just a comment about what is covered by insurance. He said here, so LPS is covered by standard insurance, but not surges. So he's just talking about what, yes.
Insurance on a big solar, big utility power plants, it's quite a niche industry. So you get different types of insurance. I'm not that across all the different offerings at the moment, but you get business interruption insurance, which covers the loss in generation revenue from you not being able to produce power. And then you get the insurance that covers the equipment that gets destroyed. So I have heard, you know, that with the early round, say, projects that didn't perhaps have as much lightning protection as they should have in those very lightning prone areas, that the assessors have become very strict on diligent lightning protection system designs, as well as proper risk assessments being done. So I know that that has become a requirement for insurance cases for big solar or big power plants generally. And the business interruption insurance, because it's a very costly insurance, given, especially in these very big plants, that has a whole number of other requirements that you've got to meet, as far as I understand.
A question here from Tumaleng. He's saying, any movement in terms of addressing the grid capacity constraint? I mean, Eskom transmission launching, I mean, I heard rumors of funding coming from the Green Fund being used to capacitate transmission expansion. Is that actually materializing?
So I think that is the biggest focus at the moment of this industry with Eskom. And that conference that I mentioned a few weeks ago that we attended with the other IPPs, a big focus of that was on things like how we allocate capacity, the process of allocating that, because that was purely dealt with in the Eskom domain. We had no insight of how they, you know, if you have 5 projects competing for 100 megawatts of capacity at substation X, how does Eskom decide which one of them they give that capacity to? And there was no defined process for that, and there is movement now towards doing that. In terms of allocating grid capacity in the areas where there's very high resource in the Northern Cape, the problem is we need the interconnectors to be strengthened, or we need load, we need big batteries to be built in those places. So the ESI PPP that's just been released has allocated storage capacity to a number of substations with very high, in very constrained areas around the Northern Cape specifically. So that's one move that is moving towards strengthening that. The challenge is the interconnectors are the biggest problem. So those 400 kV lines in and out of the Northern Cape, Eskom really needs to build more lines in and out of the Northern Cape. But the problem, as I understand it, is to build a line that long, you need to cross so many different plots of land that each plot that you get to, you've got to negotiate servitude rights and whatnot to get that line built across. And that is such an onerous approach to try and get something built that it gets backlogged for years, which is why the TDP has all these wonderful plans in them, but they aren't necessarily executed. So that's one of the big challenges with building the transmission infrastructure into the Northern Cape, is the sheer number of land parcels that you've got to build it across. And that's the 400 and the 765s that are affected by that. And of course, the biggest fundamental issue is that you'll have your load center that is always going to be in Gauteng and Cape Town, and then you've got generation from very far away. So you've got to work around that. And at the moment, there's just a shift to try and bring more of the solar generation and wind up towards the other provinces where there's load. So yeah, but it is front of mind. I think the unbundling with Eskom, I should have maybe added that to my presentation, is absolutely fundamental to unlocking this. So if Eskom transmission is split off and operates separately to generation, Eskom generation, it will enable transmission to have access to finance to build some of these projects, which at the moment they're subject still to the same credit issues with being lumped with the full Eskom group. So until that is done and fully allocated, they are struggling to move.
Okay, so what I'm going to do is I'm going to ask that there are no more questions posted. I'm not going to answer any questions from here on in if they're newly posted. Craig, we've got 5 minutes and there are roughly about 4 or 5 questions to go. I think let's constrain the answers to 1 minute and see if we can get through them. So there's a question here from Carl Neptune, ex-Pragma. Is there enough being done by IPPs or owners or the EPCMs to ensure good whole of life asset management? Good question. I know we looked at this extensively.
Yeah, I think it's very important to consider that now, especially with the plants that are approaching midlife and midway through your PPAs under REAP, which is a 20-year timeline. I suspect a lot of them are now looking at extending those, or the potential of extending those contracts. And with that comes an understanding of what maintenance has been done and how you then manage it going into what is a very unpredictable next decade, say, to 30 years of plant behavior. So the clients that I've seen and have worked with generally look after their assets. I think the procedures probably have a little way to go in terms of having them standardized and done, knowing Carl, I think it's that ISO 90,001, I can't remember the standard for that asset management program. So getting there, not there yet.
Okay. The next question is from Dwayne Breitenbach. It's around equipment obsolescence. Is there an effective strategy to tackle this? Is there something that engineers or EPCMs can do to mitigate? And is there like a percentage of modules that are kept as an industry standard as spare, or are suppliers obliged to keep a spare holding or protect against obsolescence?
Yeah, that's a good question from Dwayne. So the biggest strategy from our side, I think, when we design the plants is making sure, take an example of power plant controller. We've had a power plant controller on a project that recently the OEM disappeared, and the EPC at that stage didn't hand over the documentation and the information for how that PPC actually operated and what the programming was. So to now go and replace it with something new and unpack what is a very complicated piece of equipment has taken a very long time and is a very onerous process. So I would say the biggest lesson for doing designs around equipment obsolescence is ensuring that if you're going to do, say, a string inverter arrangement plant, make sure that you have modular blockwise designs that don't have bespoke 10 square millimeter DC cables, something like that, so that if you do have an inverter that is no longer available, you can quite readily find another one that will at least fit what is considered a relatively standard design. Same for communication, same for tracker systems. You're going to struggle otherwise, I think, with retrofitting new equipment to old plant.
Okay, let's move on here. Is there preference for 1,000 or 1,500 volt DC PV arrays?
1,000 volts are building standards. That SANS 10142 that dictates you can't have more than 1,000 volts in a building environment. So fortunately, we're stuck there on buildings. 1,500 volts is the move a few years ago for utility scale, and the high voltage is preferable because you can allow longer strings that actually bring it down. So it's preferable to go for a high voltage. But it's just a safety issue for buildings.
Is there any consideration around the recycling of end-of-life panels? I mean, we're pumping lots of these into the world as we know it. at the end of life, what happens to them?
That's the next business idea that I leave open to this audience, because there's going to be a lot of them floating around, and at the moment I don't think there's anyone that's doing much about it. So glass you can recycle, the aluminium is the most recyclable part. I don't know what you do with silicon and the rest of it. So yeah, business idea for those who want to capitalize on 5 gigawatts worth of decommissioned plants.
What percentage we've got? Okay, we're going to end off with this last particular question. So Dexter, you've got it. What percentage of the initial project cost would be advisable to allocate to the maintenance contingency cost for useful plant life?
You mean in terms of percentage of capex that would be allocated to an MRA, a maintenance reserve account? I think, rather than a flat number, what you'd want to do is have a proper strategy in terms of spares. No inverter is going to last 20 years. So that the fact, so you're going to have to refurbish or replace, as an example, throughout that 20-year timeline. So it can be built up. You would need to build it up with an appropriate strategy, I think, rather than a flat assumption. I think it would just depend on what technology and configuration you're trying to use, but that would probably be the best approach.
So it's a classic case of spend the effort up front to understand what you're doing for the rest of the life of your project, and you'll save a lot of money on the tail end of it.
Yeah, do a proper design so you don't have to spend your MRA.
Okay, that's a free sales pitch. Okay, what I'm going to do there, Craig, is I'm going to close the session down. I really want to thank you and also the audience. I see we've kept virtually 95% of the audience stayed on, so you couldn't have been that boring. Well done, Craig. And just to thank the members and non-members who joined. This is where I do a little bit of an SAIEE punt. There in the handout section, there are a couple of events that I'd like to draw your attention to. On the now where are they? I did open them up, but on the 2nd of May, there is a breakfast that we are hosting. Professor Jan de Kock, the current 2023 SAIEE president, will be doing the keynote address there. And it's going to be looking at load shedding. The question is, can South Africa be saved? Which is very topical. And we've got Sabu Charlie, eThekwini's energy transformation journey, will be presenting, and I'll be looking at issues around sustainability as well. So there are a couple of discussions at that breakfast. And then there's a really interesting discussion on the 9th of May, which we'll be looking at. We've got representatives from Adams and Adams, Vishent Pillay, who is a partner there, will be presenting around sort of the IP, intellectual property, and the impacts around energy security, innovation, sustainability. So specifically IP developed around a lot of what we're doing. I think that'll be also very, very topical and interesting. So that is coming up. And there are a couple of other, what's now is free. You can take it off the handouts, and also access to the Training Academy brochure. And this presentation, once again, will be available from the SAIEE TV channel, and a notification will go out when it's been posted. That brings us to the end of this presentation. We are going to go in to an AGM for this KZN Centre. Craig, I want to thank you for your time. You do not need to hang on. I think you've done your duty and done it well. So thank you very much on behalf of the SAIEE and the audience that have participated here today. A big thank you. So Minx, I'm going to hand over to you for further protocols in terms of the SAIEE, and I'm going to switch